Hello viewers. Today I am covering number system and codes. This is a very important topic in computer organization and architecture subject because in digital computer we use binary number system, and for its compact representation we use a hexadecimal number system. This number system is little different from the decimal number system what we use in our day-to-day life, and later topic of computer organization and architecture like the floating point number system, error detection and protection code, and memory addressing in assembly programming. They all will be using this binary number system or the hexadecimal number system. So it is very important that we learn this first before we can cover those topics. So let's start from the beginning. So here I am introducing the number system. You know that the decimal numbers are written like that, like this 987.34, and with a subscript 10. It means it is a decimal number system, and the point is called the decimal point. In binary number systems there are only two digits, 0 and 1. So it will be a string of zeros and 1, like here 101.01 with a subscript 2. It means it is a binary number system, and the point here is called the binary point. Now this number in positional notation, you can see all these digits have their position starting from 0 just before the point 0, position 0, 1, 2, 3, like this. And after the radix point, this point is actually called the radix point. After the radix point, the positions are -1, -2, -m, etc. So for decimal number the radix is 10, and for binary number the radix is 2. So uh, not only they are indicated with their position, these digits, they also have some polynomial notation by which we can know what is the value of the digit 9. Okay, so we, as we call 900, so we know that the value of 9 is 9 times 100, right? And the value of this 8 is 8 times 10, and value of 7 is 7 times 1. So all these positions have their positional weight that is given in this polynomial notation. So this is the digit multiplied by the radix. So if it is a decimal number, it is 10 to the power n minus 1. So because this 9 for this decimal number, its position is second, because we are counting from 0, right? First position is 0, then 1, then 2. So it will be 9 times 10 to the power square plus 8 times 10 plus 7 times 1. So this is the integer part. Now the fraction part, they are in according to the polynomial notation. It will be -1 here after the radix point. So it is 3 times 10 to the power -1 plus 4 times 10 to the power -2, like this. So here another example is given with a decimal number 251.41 with a subscript 10. That means its value is 2 times 10 square plus 5 times 10 to the power 1 plus 1 times 10 square plus 4 times 10 to the power -1, because this 4 is after the decimal point, plus 1 times 10 to the power -2. Okay, this is the way to find its value. Similarly, we can find the value of this binary number. So it will be 1 into 2 to the power 2. So this is 4. And here it is 0, no? So the 0 times 2 to the power 1 is 0. And then it is 1 times 1. So the total here in the integer part is 5. And then it is coming 0.1 times 2 to the power minus 2. So it is 5.25 in decimal. So here it is giving another number. You know the binary digits are 0 and 1. So binary numbers are a string of zeros and 1. So here it is a big number 11010.11 with a subscript 2. So if the subscript is given, you know it is a binary number, because otherwise it could be a decimal number also, no? By default, no subscript, we can consider it as a decimal number. But with the subscript 2, it is a binary number. So let's see what is the decimal equivalent. So this one, 1 times 2 to the power 4 plus 1 times 2 to the power 3, like this you compute, and it is coming out to be 26.75 in decimal. Okay, and 2 to the power 10 is 1024 if you compute, and this is called K or kilo in binary number system. 2, 2 to the power 20 is this big number which is called mega in binary number system, and 2 to the power 30 is this big number and it is called giga. So other number systems are also similar. So in octal number system, the base is 8, and there are 8 digits are there starting from 0, 1, 2, 3, 4, 5, 6, 7. So this number, if the subscript is given as 8, you know that this is an octal number. If no subscript is given, by default, it can be a decimal number also. It cannot be a binary number because of 274, but it can be a decimal number. But when the subscript is given, you know that it is an octal number. So what is the decimal equivalent of it? It is 1 times 8 square plus 2 times 8 to the power 1 plus 7 times 8 to the power 0 plus 4 times 8 to the power minus 1, which is only 87.5 in decimal. So hexadecimal number system, there are 16 digits are there. So the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it is A, B, C, D, E, F. Total 16. And the value of F is 15. So from here it is 10, 11, 12, 13, 14, 15. 0 to 15, total 16 digits in hexadecimal number system. Now this number B6 5F with a subscript 16. It is a hexadecimal number, and what is its decimal equivalent? You know B is equivalent to 11. So 11 times 16 to the power 3 plus 6 times 16 square plus 5 times 16 to the power 1 plus 15 times 16 to the power 0. So this is 46687 in decimal. Okay, so viewers, you can also pause the video and have a detailed look of this slide. So let's write the numbers, decimal number system. It's only few numbers are written from 0, 1, 2, 3, 4 up to 16, and its binary representation is also given here. You can see 16 is 10000. So to write a number in binary, we are using 5 digits, whereas in decimal it is 16. So binary representation is not very compact. So that's why to refer something we use the hexadecimal number system, but digital computer understands only zeros and ones, so but they use the binary numbers only. But for our sake, we use the hexadecimal number system or a octal number system for compact representation of a big strings of zeros and ones. So this is the equivalent octal numbers are given, and equivalent hexadecimal number is given here. So let's do binary arithmetic. Binary digits are only 0 and 1. And let's see the addition. If you add 0 plus 0, it is 0. 0 plus 1 is 1. 1 plus 0, 1. 1 plus 1 is 2, right? In decimal. But in binary, it is written as 1, 0. Okay. So that is for single digit addition. Now let's see an example with a big number. First number is called the oggend with what you are adding, and the second number is called the addend. So you know how the addition goes on, just like decimal number addition. We start from the least significant digit and keep going to the left hand side to the most significant digit addition. But every location can have only in the result have only one digit. But if the result is two digit, that most significant digit goes as a carry. We call it carry. So let's see the addition. 1 plus 1 is 2. 2 in binary is 1 0. So out of that 0 we write here, and 1 goes as a carry. Now we are adding this 1 plus 1, again 1 0, 0 here, carry here. So here in this column it is only 1 1. So here it is 1. Here again 1 plus 1, so 0, carry goes here, and then again 1 plus 1, 0, 1, 1 plus 1, 0, 1, nothing is here, so it comes here. So even the oggend has only 6 digits, but the result has 7 digits. So when we are adding numbers, the data word should be enough to keep the extra digit. There shouldn't be any overflow. Otherwise, the result will be wrong. Now let's see the subtraction. We know the borrowing concept from decimal number subtraction. So when subtracting, we keep the big number as minuend and the smaller number as subtrahend. And let's minus 1 minus 1 is 0. Now 0 minus 1 cannot happen because 0 is small than 1. So we have to borrow. If we borrow from here, this digit will become 0 and that 1 will come here, which is equivalent to 2. 2 minus 1 is 1. Now 0 minus 0 is 0. Again 0 minus 1 not possible. And here there is no 1 here, no? So you cannot borrow from here. You have to borrow from here. So with respect to this location, this is uh, 4. So you are borrowing basically 4, that you are distributing 1 here, which is 2 plus 2, 4. And this digit will become 0. So now 2 minus 1 is 1, and 1 minus 1 is 0 and 0. Okay, so this is the result. Let's see the octal arithmetic. Octal digits are 8 digits, 0, 1, 2, 3, 4, 5, 6, 7. So we will be minusing, adding oggend with addend. So 1 plus 4 is 5. 7 plus 5 is 12. So 12 has 12 in octal. 12 in octal is 14, right? So 4 you write here, 1 goes here. Now you are adding this column. 4 plus 1, 5, 12. 12 in decimal is 14 in octal. So 4 goes here, 1 goes here. Then again 5 plus 1 plus 3 is 9. 9 in decimal is equivalent to 1 1 in octal. So 1 goes here, 1 goes here. That 1 comes here. So this is the result, octal result. Now for subtraction, uh, we cannot do minus 3 from 1. We have to take a borrow from here. If you borrow here, this 5 becomes 4, and this 1 0. 1 0 is equivalent to 8, right? 8 plus 1, 9. Total 9. 9 minus 3 is 6. And now 4 minus 4 is 0. Again, you cannot do 4 minus 6, so you have to take a borrow from here. So this 7 will become 6, and this 1 0 is 8. 8 plus 4 is 12. 12 minus 6 is 6. And then 6 minus 5 is 1. Let's see the hexadecimal arithmetic. Hexadecimal digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So we are adding 9 plus 8 is 17, and 17 is the decimal. So that equivalent in hexadecimal is 1, 1. So you keep the 1 here and 1 goes here. Now A is equivalent to 10. 10 plus 1, 11. 11 plus 5 is 16. So 16 in hexadecimal is 1, 0, 0 here. So B is 11 plus 1 is 12. 12 is equivalent to C. So you write C here, and B plus D. D is equivalent to 13 plus 5 is 18. 18 is equivalent to 1, 2. So 2 here, 1 here. This is the sum. Let's see the subtraction. 9 minus 8, not possible. You have to take a borrow. Take 1 from here. So if you minus 1 from B, it will become A. And this 1, 0 is equivalent to 16. 16 plus 9 is 25. 25 minus 13. It is 12. And 12 is equivalent to C. Okay, now you are minusing. A minus 0 is A. And then again you cannot do 5 minus 8, so you have to take a borrow. If you borrow from A, it will become 9, and this is equivalent to 16. 16 plus 5 is 21. 21 minus 8, how much? It is a B, 13, and here 9 minus 5 is 4. Okay, so let me solve some other binary number additions. I will be solving it so you can get more clear picture. Let's consider two binary integers. Number 1 is 10111. I want to find out what is its decimal equivalent. So we know their positions: 0th position, 0, 1, 2, 3, 4. So their weights are given 2 to the power 0, 1, 2 to the power 1 is 2, 2 square is 4, 2 to the power 3, 8, 2 to the power 4 is 16. So this number is 16 plus 4, 20, 20 plus 2, 22, 22 plus 1 is 23. And let's consider the second number. It is 011110. So here it is 8 plus 4, 12, 12 plus 2, 14. So this number is 14. Okay. Now let's do the binary addition. So these are the number. Number 1 is 11001, and number 2 is 01110. Okay, so let's do the addition, and then we can quickly verify with their equivalent decimal numbers and their addition. So this is 1. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 0, and there is one carry here, 1. So this is 1 plus 1 is 0, and this one goes here. Okay, so let's see their decimal. So the first number is 16 plus 8 is 24. 24 plus 1 is 25. And the second number is 8 plus 4 is 12. 12 plus 2 is 14. Now let's see this number. This is 32 plus 7 is 39. And you can also verify that the addition of 25 plus 14 is 13. Let's see another addition. 1 plus 0 is 1. 1 plus 1 is 0 and 1 carry here. Again 1 plus 1 is 0 and carry goes here. 1. 1 plus 1 is 0 and carry goes here. Now it is 1 plus 1 plus 1 is 1. 1 and here 1. We will verify after getting their equivalent decimal. So this number is 16 plus 3 is 19, and the second number is 16 plus 8, 24, 24 plus 4, 28, and 2, 30. And the result, as we have computed, this is 32 plus 16 is 48 plus 1 is 49. Now verify with their decimal addition. So this is correct. Now let's see binary number subtraction. So here the first number is 110010 and the second number is 1110. So for subtracting, you can only subtract from a bigger number. So the first number should be bigger, that's okay. Now 0 minus 0 is 0. 1 minus 1 is 0. Now here 0 minus 1 not possible, we have to borrow. So from here we cannot borrow, we can borrow from here. So with respect to this position, this is 4. So if we borrow from here, it becomes 0. And then this 4 we can adjust to here and 1 0 here. Okay. So 102 minus 1 is 1. Then here 1 minus 1 is 0. And for this we have to okay, so 1 minus 0 is 1 here. Now this 1 became 0. 0 minus 0 is 0 and here it is 1. Okay, so let's see the decimal equivalent, then we can verify that our subtraction is right. So the first number is 32 plus 16, 48. 48 plus 2 is 50. And the second number is 8 plus 4, 12. 12 plus 2, 14. Now let's see the result. This is 32 plus 4 is 36. So we know that 50 minus 14 is 36. So our computation is right. Next time I will be covering hexadecimal number addition and subtraction. See you then.